All right, friends and neighbors, it's time now for part 5 of our voice over IP journey. We are going to talk about RTCP this time. So far we've talked about codecs, right? We catch the video or the audio, we encode it using samples, and then we provide values for all those samples, and then we put all of that stuff in a packet and we prepare it for transmission. We talked about all of the processes that are in there in the codec, and then we talked about some of the major codecs. Probably the biggest one today is G.711. It's the one for the traditional telephony network. Okay, so then we talked about how to packetize all of those voice samples. And for that, we used the real-time transport protocol. So that was originally in RFC 1889 and now in 3550. We also know that those kinds of packets have a particular payload ID, and RFC 3551 provides the profiles for all of the different codecs that were used traditionally. Today, of course, we have many more codecs than were originally put into the tables in RFC 3551. But that aside, we had the codec, we did the samples, we put those in a packet, we sent those across the network in RTP. Here is an example of one of those particular kinds of packets. We can see all the way down here at the bottom is the payload, but of course we can't read that unless we decode it with something that understands the encoding of the codec that was used, in this case G.711. Alright, now wouldn't it be kind of cool if we had a way to measure how well this call was going, right? What was the quality metrics of the call? And for that, we're going to use another part of RFC 3550. So RFC 3550 also includes the real-time control protocol, or the RTP control protocol. And so we'll do a little bit of reading here. This will be a little clunky, but here we go, right? The primary function is to provide feedback on the quality of the data distribution. So what we're trying to do is measure how well this call is going. And remember that we're really talking about packets going across the network. So this is an integral role of RTP's transport protocol function. So RTP is not just about wrapping up a bunch of voice packets and sending them across the network and telling you, how the data was encoded. It's also about measurement. So why would you want to do that? Well, we might have some kind of adaptive framework. In this case, it's talking about encodings. It also might be a way to help us identify problems with the infrastructure. And an important part of this is that it's not just what I'm sending to you, it's your perception of what I've sent. So we have something called sender reports and receiver reports, and we have a way to keep all of that stuff together. Now, RTP and RTCP are in the same RFC, so they're designed to work together. So in a perfect world, what the RFC says is supposed to happen is that RTP is going to take a particular port number, and then the RTCP stream associated with that is going to take the next port number. You can see that here. I've highlighted an example where we've got port 2800 in RTP and then 2801 in RTCP. Now below that, we can see that the RTCP packets are interspersed inside RTP. So what ends up happening is that when you are in the middle of a voice call or a video call, there's lots and lots of data packets going, lots and lots of RTP. And then every once in a while, boop, you see a little RTCP packet. And then lots more RTP goes by, and then boop, there's another RTCP. Because it's data about the data. So we're trying to keep track of what's going on along the way. Now you might be saying to yourself, well, wait a minute, what if we have a lot of senders and a lot of receivers? How do we keep track of all that? I'm glad you asked. So we have a lot of message types, and we want to figure out some way to not only have the messages tied together, but separate out all of the data for all of the different streams. And so every sender generates sender reports, every receiver generates receiver reports, and everybody's got a source description that identifies who they are. And then, of course, we've got some other message types that sort of make sense. Now, another idea here is the idea of compound packets or compound packets. And that just means that we're going to piggyback packets on top of packets. And so a single message can have multiple packet types inside it. And here is an example. So this particular RTCP message has two kinds of message inside. It has a sender report and a source description. Now the source description is important because this ties us with a particular endpoint or person maybe that logged in. And then we've got all of the details associated with a particular message. Now right here we've got a little foreshadowing of what we're going to talk about next week, and that this stream was set up by H.245. That's part of a signaling protocol. We have the same way to do it in something like SIP. But what we're going to do here is identify the person or the node that sent this, and then we're going to provide a report about the data, which is the sender report, which is not expanded in this particular slide. So here we go. So this is an example of sender and receiver reports. I've closed the source description this time, and here we're going to look at a sender report. So this is a different code for the message type. Makes sense. And what are we sending? Well, we're sending the data chunks that we sent, how much data. So the how much data is going to be in packets and octets because, right, a single packet will have lots and lots of data in it, and we might even have more than one voice packet in there. But importantly, we've got the timestamps, which really gives us a way to measure the quality of our call and the latency or the delay associated with a particular stream of messages. Now, it's not always the case that a vendor's implementation actually uses RTCP. Some proprietary solutions actually use their own messages. So Cisco Skinny is a really good example. They have their own message reports that describe the performance of the call. Now, another thing that's important to realize is that, great, we sent all this data about the call, but where is it all stored? Well, a lot of times we can get the information on the call server. So if you have access to the call server, you can go in there and do the debug messages or the statistics messages about the calls that are in progress. But in many cases, we can also develop a picture of what's happening by looking at feedback on the phone itself. So many VoIP phones have the ability to show you some amount of quality metrics right there on the screen of the phone. And then lastly, if you capture the call, the packets, you can actually use an analyzer such as Wireshark or OmniPeak to show you metrics about the call. And in this particular case, we're talking about an analyzer, so they have lots more detail about what's going on with the individual calls that are running across the network. Now, I thought since we're closing out RTP and RTCP, I would add just a dash of security here. It is possible to encrypt RTP and RTCP. It's a pain because you have to get certificates around everywhere, and a lot of this stuff is internal. And if you're VPNing, you're already encrypting. So if you're offsite, that's probably what you ought to do. But there is a mechanism to handle this. Now, most folks don't do this, right? Because if we're internally and we don't want to worry about the problems associated with trying to get all this stuff set up. But there are extensions to both RTP and RTCP that are secure. So this is an example of the right from the RFC, what it looks like. And we can see that I've highlighted the encrypted portion. And what this really means is that the header is not encrypted. So all that we're encrypting is the payload. So a bad guy intercepting this would not be able to decode this. Now, the other part of this is that the authenticated portion. Remember that when you do an authentication code, you're just doing a mathematical calculation. You're adding a number or appending a number, and the entire message is authenticated. So two different approaches to security there. Secure RTCP does the same thing. We've got an encrypted portion, which is the data portion of the message, and then the data portion and the header are authenticated. Well, I think that'll wrap up RFCs 3550 and 3551. So remember that the related ideas together here are the codecs, RTP, and RTCP. And there's a vast collection of codecs. They include audio and video codecs, We mentioned the ITU-T G series for audio and the H series for video, but of course there's the MPEG standards. And then, if we have time in this series, we'll also talk about what's happening right now with some of the stuff for web and stuff like that. But we have a problem. All of this stuff is talking about transport of audio and video, which is great, but how did we get to sending stuff across the network? How do we make phone calls? How do we figure out who we were trying to call? How do we identify ourselves? What about the node itself? Well, the answer for all of that is the signaling protocol, and we will talk about that next time. So thanks for watching, thanks for listening, like and subscribe if I helped, and may those packets always reach their destinations. And don't forget to measure them via RTCP.